Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about geometry, dimensioning and tolerancing. Geometric dimensioning and tolerancing, or GD&T. So let's dive deep into it. So what exactly is the problem? Well, the problem did not started until we reach industrial revolution, because before that everything was very in-house, so to say. So basically a company used to make things, but everything was in one place. So the person who is designing it, the person who is machining, or sometimes it could be one person who is doing it very slowly. So there was no issue of communication. But once we reached industrial revolution, we started to create an ecosystem where we supposed to, hey bro, I want this axle to fit for this. You're supposed to be able to tell someone else. And then we realized communication is a hell of a beast. The problem is like, what do you mean by 10 millimeters? I'm like, wait, doesn't 10 millimeters say? Well, in perfect infinite world, yeah, it will be 10 millimeter. Real world is not like that. Real world is not perfect. So, and CAD made it worst. That is a recent thing, is that CAD is a mathematical world inside a virtual world. So once you go there, it's like, you want 10 millimeter? It is 10 millimeter. It's like, bro, 10 millimeter does not exist. It's like, if you look into the mathematics that is going into the virtual world that are making these things, it's perfect. It's like, zoom in, 10 millimeter is 10.000000. There is no plus and minus. It will go infinity, is perfect. Now, here's the real world is not perfect, meaning 10 millimeter means 10 millimeter plus and minus certain extent. So it could be 9.91. It could be 10 0.01. So there would be some tolerance. Or it's a really good part. It could be 10.001. Or it could be 9.991. So there will always be a flex to it. There is always a give to it, a tolerance to it. And that created the communication issue. Basically, the moment we are like, hey, get this part manufactured there and we're going to assemble it, get this part there to improve your production output, and then you got all the parts, none of them fit with each other because they are not communicating properly. Meaning the 10 millimeter of one is like very precise, absolute. 10 millimeter, who cares, you know, that 0.000, that plus and minus, that's the hassle. So that creates an issue. We do not live in a world where we have 100% perfect infinite precision. So that creates an issue. And you must specify basically how the CNC machine works. It has a very lot of what you call flex in how it works. Basically, if you want a rough and dirty part, boom, boom, take and go. But if you want really precise part, then again, you're gonna do a lot of tool changing. You're gonna optimize your tool path. All of those things have to be done. How the heck you communicate that? So that is the problem. The communication breaks down. The moment we want to like, hey, make this, as long as everything in-house, you do not even notice that this is a problem. The moment you're like, okay, let's say this country is going in tariff, we're gonna take the factories out and put it somewhere else. You would be shocked. The things that were working no longer work simply because it's not fitting together. So there is a genuine problem that we must take care of. So the first iteration, Mach 1 iteration of this technology was tolerancing. So basically, machines can never have infinite precision. You may be like, okay, but we can make 10 millimeter. Yes, 10.0, that's like, we got this, we good, we got this. But what about 10.001? Okay, well, expensive CNC, but again, we got this. What about 0.0001? Now you are going into EDM territory, and not to mention expensive EDM territory. Normal EDMs can't even do that. Not because like the technology can't do that, it's that their motion system have to be that refined and that precise. So that creates a scenario. We cannot achieve infinite precision. So the most precise machine is generally lithography machines that are utilized. They literally count atoms. I'm not even joking. Their ultraviolet reflection mirrors are literally atom by atom counted. That's also not precise enough. Because again, atoms are balls, so they are not precise. We have to use sub-nanometer measurements to make them as precise as possible. And then also they are luch-puch. Like, you know, they are not very tight, so to say. So we always have to specify need and some tolerance, and you need to have it, because worst case scenario is you do make it. Like you're like 10 and somebody made it 10. And then either A, it will not fit, or worst case scenario, it will fit and then jam. And then it will be useless. So you're like, okay, I'm going to fit this. And this is like perfect bearing and perfect. And it's like, it's not gonna work. So it will jam up. So we have learned it the hard way that you must give something. And be mindful, if you are doing it properly, you will also account for temperature. For example, this aluminum part goes into the steel part. What is the thermal expansion of steel versus what is the expansion of aluminum? And you have to figure things out. So it's one of those things that you must account for it. And when you're making large batch, it's one thing. It's like, let's say a designer made something, an engineer working on it manually, physically going and double checking everything, he could use his own intuition to fine tune it and make it a fitment. But the moment you go batch processing, this sort of up and down is not allowed, where it's like, no, one person is going, methodically building it. No, that is no longer possible. So what do? We do min max. Basically, what is the minimum, what is the maximum allowed, so it can work intended application. So for example, you can have a clearance fit, you can have interference fit, basically and then you can have transition fit. It's like okay, so you have to specify that, like, what do you need? Like, do you need this pin to be locating pin? So you will focus on interference fit, because once you put it, you do not want it. But do you want it to be like a bolt, and you are using spring tension to lock it down? Then you're going to focus on clearance fit. Or sometimes you just want, like, it may have to be rotated once in a while, so it's like, okay, transition fit. Again, you have to figure it out based on your application, based on the material property. This has to be taken into consideration, so to say. And if you do not, this will happen. Things will not fit up properly. So we define min-max, and the easiest way to spot min-max is like, either there will be two dimensions. For example, you have one dimension that says 39.5 and another says 39.8. What the hell? That simply means make sure that it does not go below 39.5 or above 39.8. They are giving you a range. And sometimes it will be like 20. It's like, okay, 20 means 20. No, 20 means 20 plus and minus 0. So it's up to you. So that's how we started to approach basically 1950s to 70s. So this is how we created the tolerancing world, where we're like, okay, you want your part, I got this, I'm cool, but please define tolerance. Basically, how tight it has to be, how loose. Basically, a piston, it has to be giving, it has to be, it cannot be a transition fit, nor it can be interference fit. It has to be a clearance fit. Now, here's the deal: how tight of a clearance you want, because if you have too much clearance, piston ring will be exposed to too much pressure, and you're not converting a lot of motion. But if it's too tight, any sort of minor deviation, temperature expansion and contraction causes issue. So you have to work around it. You have to design according to it. So tolerancing is our language where we can communicate this thing. Well, we did made a language, but it created a problem of language interpretation, basically ambiguity, meaning tolerance is not repeatable or verifiable. Like, wait, didn't we specify? Yeah, that's the whole point. How the heck you measure it? We never thought of that. I'm not even joking. Like, this was an upgrade from, okay, how somebody is working in-house to, like, okay, let's make an engineering design so new recruits can work it. But this created issue. Basically, unless new recruit but taught by old ones, they will be like, what the hell is going on? They have to waste a lot of parts to relay. Oh, that's what they meant. So there was a lot of ambiguity because it was not repeatable nor verifiable. It's like, what do you mean? I'll explain further. So same sketch, take a sketch, and that is made by the old language of tolerancing. And again, people made things with it. It's just that the moment you take that same blueprint to give it to other people, outcome would be different. Parts will not fit. So let's say an engine has like 8 design diagrams and 8 assemblies. You can give 8 assemblies to 8 different manufacturers, nothing will fit. Because again, this diagram is too sloppy. It has too much room for interpretation. So size and position is defined. That's cool, awesome. But there is no data for what the heck do you mean by the forum? What do you mean by location? What is the tolerance on those things? So it's very, you have to already know what you're looking at. That's the problem with this. You have to know what you're looking at. And so how do we solve it? Well, for example, let's say this is a U-joint, right? It's a U-joint, but here's the deal. How does it supposed to be utilized? If you are an in-house manufacturer, you know, hey, we are footing assembly like this. So you will make sure the machinist will know that, hey, let's make sure this is machined right. This part, okay. But here's the deal. You give this part to someone else and they're expecting you're going to go like this. And they're like, okay, they're precise with this, but they're not precise. You bought it, it's jammed. So that creates an issue. So this was the issue. How do we solve it? Well, we created the worst thing, which was a giant text block. We started to put text blocks, basically. Oh, this cut has to be this thick. And then you're like, okay, make sure this face is parallel to this face. And it's like, okay. So we started to, like, as long as you have very few words, this was a system from 1950s to 1970s, is that people, first they started to write whole essays there. Then like, no. The bigger the essay, the worst interpretation would be there. So use as few words as possible and do not have ambiguity in it. So that's how we tried to do. But again, best case scenario is still vague. So it still had that scenario where it's like, oh, you have to work with them. It's not like take this blueprint, done, go home. It was not like that. It was like, take this, have a conversation, what the hell they meant, and then make 1 or 2 parts. Then you're like, I get it now. So that ambiguity is the issue. So you may think, like, you look at the sketches like, oh, this is GG. No. This is a good, like, again, compared to where you used to be, this is good, but no cigar. Let's just put it that way. So And again, many times that's why people are, old machinists can do it. Yeah, that's because they knew what the heck you are expecting. So whenever interns come in, on worst case scenario, old have already retired and intern just comes in, company's productivity goes and people are like, why is this happening? It's like, because this is ambiguous. You may not think about it, but it is ambiguous to someone who already does not know. So this was the big hurdle in 70s. So then we invented GD&T. Basically, it's a new engineering language. And the idea with this language is that we're going to create a symbol, we're going to create an index of those symbol, and we're going to create a standard, and we're going to remove all doubts. Meaning, if you use GD&T, the end, there is no discussion. Meaning this mechanical part will fit this mechanical part, the end. You remove every single bit of ambiguity. That's why you will find something weird. There is no dimension in that. Basically, the diameter, like it was like, what is the diameter? They're not even specifying that, because again, that can come from normal general design. So it's like, oh, it's a 10 millimeter. Okay, but you do not want that. You know 10 millimeter, but here's the 10 millimeter plus 0.14. That's the tolerance allowed. And then you can have a modifier there. Do you need that? Like you can specify, there are certain, what we call modifier categories. You can be like, for my application, I would like this sort of modifier if I need it. Mostly you won't, but again, if you need it, you can have it. And then you're going to have primary datum. And this is where things changed. Basically, datum allows, like, this is your primary. Make sure this part is right. For example, let's say you're making engine blocks, right? How do you know which is the most important part? Well, we are working on it, so we are learning the hard way. Is that when you are taking engines, you make sure that gasket block, that's very flat. That's flat AF. But again, it's a casted thing. So we make sure that everything else is relative to that flat surface. That puppy has to be flat. Then we can make sure that cylinder head is also flat. And then these two puppy make love together properly. So that's how we'll design in GD&T. We will say A, this is your primary. And then we're going to say B on the side and C on the bottom. If there is oil pan, we're going to put B on the oil pan or C on the oil pan. Again, if you have a lot of stuff bolting on the front side, that will become B. And if you have some stuff going into bottom, C. So they are also done in priority wise, meaning A is generally supposed to focus on highest priority and also measurement point. So you measure from A, then you double check from C, then you triple check from C. So A, B, C, that's why they have that. And again, if you are a good user of GD&T, it will always be in serial number A, B, C. You will not have a B, A, C. You can do that. Technically, it is allowed, but it's a very bad, design. Because again, if you do that, somebody will make that mistake. So datums allows us to figure out which surface is important. And again, when you must have seen people in YouTube where, like, they have a surface plate, they polish it and then put things and then measure it. Which surface you're supposed to use? Datum takes care of that part. It's like, use A datum. And again, it has whole, basically data taken care of. Basically, I would urge you to download this system. This is from GD&T basics.com. Give them your email. They're going to give you this awesome PDF. Be mindful, it's huge. I thought I could print and read. Yeah, in A4 you can't read. A3 maybe. This is a huge print. So if you're in a college kind of deal or a ITI sort of institution, you may want to print it large. And again, surprisingly detailed. Everything is in there, like size, location, orientation, form, all of that is there. Because it is a language. So you have to, like, okay, profile of the surface, profile on a line, position, total runout, circular runout, angularity, perpendicularity, parallelism, flatness. And again, that's the talk. Make sure it's parallel to this. No, we will not do that. We'll just give the symbol, and then we'll have make sure A is parallel to B. Done, go home, sweet dreams. So that's the whole point. This is a whole language that we have built, like, this system, and it can define everything within reason to every industry. Meaning, I'm working with aerospace, you're gonna use the same thing. I'm working with a large industrial foundry machines, it's the exact same language. This language is universal. Meaning, if somebody made this correctly and somebody interpreting this correctly, meaning they are trained to GD&T, your part should match. Meaning, there is no, oh, I'm building this in Mexico and I'm take the part that I'm going to assemble it in India. No problem. It should fit. If both of them are following GD&T properly and there is no oops in the GD&T, the data will match and both parts will make love properly. So you can literally, hey, I have oil pans being manufactured in Nepal for some reason. I'm gonna have, like, piston heads manufactured somewhere else, let's say Mexico, and then I'm gonna have, like, a cylinder block manufactured in Bangalore, and then we're gonna have live together. So That's the whole point. So you have to prioritize. Again, this is why it matters A, B, C, and it always has to be A, B, C. You can mix it up, and generally not recommended. It's classified as like sloppy design. So you follow this properly. Anybody who's making it properly, it works. There's whole languages there. Let that be very clear. Please download this. If you really need to learn this, please download this. I cannot recommend something better than this. And again, it's a language, so you have to practice. You cannot be like, oh, I learned it. No. You have to practice the hell out of it. Hell out of it. Because again, I'm not even touching modifiers. Datums took a lot of time. Trust me. When you look into modifiers, like, wait, what? What do you mean I have to measure from 2 points? If I cannot measure from 2 points, then it cannot apply. It's like, yeah. Because again, everything about GD&T is designed such a way that it can be tested. Meaning, does this part meet the expectation? How do you know? Well, this language tells you how you're supposed to measure it also. So that's why everything is accounted for, everything is in detail, and there are standards like, because again, I'm working in metric system, the standard for us is ISO 1101. So this standard, if your machine shop and your engineer are working with this standard, everything will be fine. You do not have to worry about it. You go to a Chinese shop, it's like, bro, I have this standard GD&T. They're like, I got you, fam. I got you, fam. Your part will work. You do not have to worry about it. It will work. So that's why GD&T language was created. Basically, it removed ambiguity. That's why symbols are used, meaning every symbol is same. Now, are there a difference between American standard and ISO standard? Little bit, but trust me, it is somewhat going from A to B is possible. Although it's not recommended to do so, because again, this thing is designed as an absolute transition error-free thing. So you may have to re-dimension it, but it can be done. It can be done. So GD&T removes oops from our machine world. So how do we utilize it? Well, it's a language. So whenever you are dealing with CAD needs certain level of trust, because again, when you are designing in computer, you can design, oh, this is a 10 millimeter part. It's like, can you trust that 10 millimeter will fit inside a 10 millimeter hole? How do you design it? You go to tolerance. Tolerance is still sloppy, so you have to go to GD&T. So how we do that? Well, first, this old system from like till now is still in use, is that you create a 2D drawing of it, and then you put GD&T data in that drawing. So you'll specify that surface is this, addendum is addendum, I'm saying datum is A, B, and C, and point from here to there, measure it. This is plus and minus. You will do that. That's on 2D layer. Basically, you take a 3D model, slice it into 2D diagrams, and do this. This is generally still preferred in a lot of places. And again, it is desirable if you are not doing everything in-house. So 2D sketch with GD&T with is a very common system. And then you have one step above, that is CAD models. So engineering company, basically like Fusion, Adobe, and Autodesk. Yeah, Autodesk and another one is SolidWorks. They realized that this was an issue, so they created MBD, model-based definition. Meaning the idea is now all that GD&T data, because it's a standardized ISO standard, they're gonna put that language into the model itself. So you have a model, and in that model you have an extra layer, that is model-based definition. In that layer you specify, hey, this hole has to have this sort of plus and minus. This hole, and again, because it's in 3D, you can rotate and look at it. So 2D sketch many times confuses people. It's like, again, if you're used to 2D, 3D will confuse you. If you're used to 3D, 2D will confuse you. So people are like, hey, because again, we are designing in 3D, CNC machine is working in 3D, why not have the dimensioning in 3D? So this was created, MBD. This is like, I think 10 years ago. So MBD is just a container. In that container, you can have sloppy things like tolerance, or precise thing like GD&T. So it's a container, you put whatever you want to put into it. And once you have done that, then if done correctly, if the pipeline is correct, you should be able to get your manufacturing part done correctly. And most importantly, whether it can be made or not. For example, you can be like, okay, I want 0.000. So far we are talking 0. Yeah, no. That extra 0 is like, no. At that point, it's like it requires precision temperature control, meaning 25 degrees Celsius is not precise enough. It has to be 25.000. And not to mention, everything has to be done in one area, because again, different materials and different expansion. So once you start to add too many zeros, it's like, it can be done. It's just that it's going to cost $1 million, so to say. So can the machine shop make it? They will read into GD&T and they're like, yeah, I got you, fam. Or they're saying, no, sir. This sort of precision we do not deal with. Again, not every part needs it. This is another aspect of engineering. You can design a part that is perfectly perfect. It's just that you're not supposed to. You only design to bare minimum. So it costs the least amount of money and it still works. So that's the whole point. The manufacturing can be done easily, and not to mention how much it's going to cost. So let's say you have one phase that's supposed to be parallel. That's supposed to be like GG. Again, you're going to have a machine, you're going to have CNC going. Then you may even put in a surface grinder and go, and then you're going to measure everything according to it, good. But if you are a sloppy engineer, you're like, okay, this size has to be this perfect, this size or 90-degree has to be perfect. Now again, your machine shop will do it, but they'll keep charging you, and you're like, oh, it's costing too much. So GD&T, good GD&T is as little as it needs to be, and as enough as has to be. Like, it has to be precise, not too much, not too little. And now we have an extra layer of it, because now we are switching from manually doing the machine to CAM, computer aided machining. People who build the software, they realized, hey, what if both of them, CAD and CAM, they are in the one package? Basically, Fusion 360, SolidWorks, Siemens NX, all of them have both of those packages. Benefit, they can read the data, meaning they can read model-based definition, meaning if you have a hole and that's supposed to be, let's say, tolerance fit, your CNC, basically CAM machine will be like, this guy wants this hole to be very precise, it's not loose fit. So he's gonna like, okay, let's make a roughing pass, then they're gonna, let's say, make a polishing pass, then it's gonna do 2-3 passes until it reaches the exact requirement, or as best as the machine can do. And that documentation will only happen between CAM and CAD, because you have MBD layer. And output should be that if it's done correctly, after 1 or 2 test piece, you should be like, this is what you want in CAD, define it properly in this, and part should be take it and go. If done correctly, it is that good. It's like, take it and go. Take it and go. So it can be done that way. And again, there is another reason for that. If you have this data in your CAD, this will go into computer coordinate measurement system, and then it can do automate. Otherwise, like, you have to take the mesh, then you have to point it and then measure it, or worst case, you have manually measure it. Again, the GD&T is designed for manual measurement. It can do all the manual measurement. But again, it was designed in such a way that coordinate measurement machine can also take care of it. It's just that they made sure that it's manually consistent. So it does not matter you are doing in Mexico, Nepal, India, Bhutan, whatever have you, it should be compatible with everything. So that's the utilization of it, meaning if done, GD&T is done correctly, you should not have issue. Like, if you know that I have this GD&T done correctly, the expert who did this, it was correct, and we send it to 3 factories, 2 factories got them right, that means the 3rd factory is not following GD&T. It's not on you, it's on them. So that's why people want to use GD&T. It removes ambiguity. It's a good tool. And if you are serious about manufacturing, you sooner or later have to learn to use this. So this was my presentation on this precise world of GD&T. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.